Welcome back to Elements of Chemistry tutorials. In this chapter, we're going to talk about electron configuration. Now, we've already discussed quantum numbers, and hopefully you watch those videos on quantum numbers because that really lends us to understanding how to do electron configuration. Electron configuration is a standardized notation that describes how the electrons fill orbitals according to the quantum theory, and it follows some very specific set of rules. The first rule is the Aufbau principle. Electrons fill orbitals of lowest energy before moving to fill the higher energy orbitals. It's like students filling up the stands at a game. They're going to fill the lower seats before they start filling up the upper seats. Okay, so you've got to fill the first principal energy level first. Remember, N is our principal energy level. L is our sublevel. N has L being N minus 1. So there's only one sublevel in N equals 1. You've got to fill that before you go to the second principal energy level, N equals 2. Here, there are two different sublevels. We have an S and a P sublevel. Then we've got to go and fill the third energy level. It has three sublevels with it, S, P, and D. Now, if you notice here, there's something a little different. You've got to go 1S, 2S, 2P, 3S, 3P, and then you've got to fill the 4S before you can go back and fill that 3D, because 4S is going to be at a lower energy state according to the Aufbau principle. So you can either learn this diagram where you have 1S, in the second level you have 2, S and P, the third level you have SPD, the fourth level you have SPDF, the fifth level you have SPDF, and continue on, and then you make your little zigzaggy line. Or there's a way to do it by looking at the periodic table that I'll show you in just a few minutes. Now, these sublevels, S, P, D, all follow some mathematical prescribed shapes. So L being 0 is a spherical shape. Remember, 2 electrons fill an orbital. So in the S sublevel, there's only 2 electrons per orbital. In the P, there are 3 sublevels. Those sublevels, remember it's going to be negative L going through 0 to positive L. So here's our -1 orbital, our 0, and our +1 orbital. And they're oriented on the axis XYZ. Now remember, there's 2 electrons per orbital. So 2 electrons will fill the S orbital. 6 electrons will fill the P orbital. You're probably getting the sequence here. Our next set of orbitals, in the third sublevel, we bring in D. Now, remember, D was L equals 2. So these are going to be -2, -1, 0, 1, 2. So there's 5 orbitals. If they each have 2 electrons in an orbital, one spinning clockwise, one spinning counterclockwise in an orbital, remember, that's going to be 10 electrons in the D sublevel. And if you notice, they kind of look like these 4-leaf clovers, except that there's a strange one here in the middle. Look at this middle one. It actually looks like a dumbbell shape with a donut running around the middle. I like to refer to these as dumb flowers and dumbbell donut to remember my D's. My P's, I think I look like peanuts, and the S is spherical. Now, when you get to F, remember in the F sublevel, L was equal to 3. So we have -3, -2, -1. Here's my 0, 1, 2, 3. So we have 7 orbitals. If each orbital has 2 electrons, one clockwise, one counterclockwise, we have a total of 14 electrons in the F sublevel. Okay, that brings us to a new rule, Hund's rule. You've got to place 1 electron in each sublevel orbital before you can pair them up with the second electron. So we literally have to put the clockwise electron in each orbital. I'm using the P as the example. before we go back in and put in that counterclockwise spinning electron to fill the orbital. Once we have one electron in each orbital, we've increased the stability. We start pairing them up, we make it even more stable. Now, these orbitals all occur at the same energy, so we call them degenerate orbitals. They're just along different orientation. And we've already kind of talked about this, the Pauli exclusion principle. Electrons must first enter an orbital with clockwise spin and then fill with counterclockwise. A lot of students find using an orbital diagram is a great way to look at it. And we can then figure out orientation. So let's pick an element. Let's do oxygen. Oxygen has an atomic number of 8. So we're going to have 8 electrons to fill in. Using our orbital diagram, we're going to have to put in 1 electron spinning clockwise, so an up arrow, paired with the down arrow. There's 2. So now we go to the 2s, 1 clockwise, pair it counterclockwise. We have 4 electrons. We have 4 more to use. We're going to put 1 in each orbital, all spinning clockwise, before we pair them up. So now we're going to have to put in our counterclockwise here. So oxygen's electron configuration would be 1s filled with 2 electrons, so 1s2. 2s is filled with 2 electrons, and our 2p sublevel has a total of 4 electrons. So oxygen's electron configuration would be 1s2, 2s2, 2p4. Let's try another one. Let's clean this out. Get my eraser to work here. There, we're erasing. Let's clean that all up. Let's pick another element. Let's do magnesium. Magnesium, Mg, has an atomic number of 12. So we're going to have 12 electrons to use. We're going to put 1 in the 1s. That one is going to be spinning clockwise. We're going to pair up that orbital with a counterclockwise spin. We're going to go to 2s, clockwise, counterclockwise, with 4. Here's 5, 6, 7. Now we want to pair counterclockwise. There's our 8, our 9. Here's 10, 11, and 12. So this is going to give us magnesium having a configuration of 1s2, 2s2, 2p6, 3s2. Okay, let's try another one. Let's continue on. We'll do something that's a little bigger so we don't have to erase quite as many on our diagram. Let's do the one at the end of the row, argon. Now, argon is atomic number 18. So we've got 18 electrons. Well, we've already got 12, so we're going to put 13, 14, 15, 16, 17, 18. Now, argon is going to be 1s2, 2s2, 2p6, 3s2, 3p6. Now we're going to talk about something sort of interesting. Argon is a noble gas. It's very unreactive. Why is it unreactive? Because its valence shell, that outermost S and P, is full. That P6 configuration is what makes argon so stable. If you remember back to oxygen, we had 2 open spots in our orbital diagram. That means it had room for 2 more electrons. That's part of why oxygen is so reactive. If we're going to use a periodic table, because drawing all these diagrams makes it a little confusing, we need to think about it, and there's a way you can number your periodic table to make this easy. First thing you're going to do is number your energy levels going down. So we're going to have 1, 2, 3, 4, 5, 6, and 7. We're going to carry that number sequencing over to this P block, because remember, this is my S block elements. Here are my P block elements. These are my D block elements, and these are my F block elements here at the bottom. Remember, helium over here at the top, it actually is an S. So we're going to carry our number system over. So that's going to be a 1, 2, 3, 4, 5, 6, and 7. Now, if we go back to this Aufbau diagram, if you notice, you have to hit 4S before you hit those 3Ds, before you fill in the 3Ds. So we're going to add that to our table. We have to do that 4S, and then this is my 3D right here. That D block starts with 3. Grab a different pencil. So we just drop it down by 1. Our F block, if we go back to that Aufbau diagram, see where F start? You have to hit 5S before you hit that 4D, 5P, 6S, then you hit that 4F. So these are dropped down another 1. I number this 4 and 5. Now something to consider here. These F elements act like they're stacked on top of each other. They all have essentially the same properties, and they fit right in that gap right there. So you're going to have to do a D1 and then go to your Fs. We'll talk about that in our exceptions to the rules. So now you just read this left to right like you're reading a book. So let's just randomly pick something. Let's pick the element right here. Okay, that happens to be the, oh, sorry, I picked a bad one. That's an exception. We don't want to do that one. Let's go to this one right here. There, oh, I'm in the right spot. That's nickel. We'll talk about the exceptions in our next video. So we're going to read this left to right like a book. We're going to have to fill that 1S before we can go on to the 2S. So it's going to be 1S2. Then we're going to fill in our 2S with 2, 2S2. Our 2P is going to be filled with 6. Our 3S is going to be filled with 2. Our 3P is filled with 6. Our 4S is filled with 2. And now we're in our 3D, and there's a total of 10. We'll go 1, 2, 3, 4, 5, 6, 7, 8. 3D8. And that is the electron configuration for the element nickel. Okay, let's pick another one, and we're going to go further. So let's do the element right here. That element happens to be tin, Sn. So to do tin, we're going to take this configuration we had before, so 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, but now we're here, we're going to fill the 3d with 10. We're going to hit 4p. Now we're going to hit 5s with 2. 4d is going to be filled with 10. And now we're in 5p, and we're over 2, so 5p2. Okay. Let's try some. Let's do the electron configuration for nitrogen. So the first thing you need to do is look at the periodic table and find nitrogen. Here's nitrogen. We're going to read it left to right like a book. 1s is filled with 2. 2s is filled with 2. Our 2p has 3. Now, nitrogen's fairly stable. Why is it more stable? Because it's 3 over. That means it's got 1 electron in each orbital. Each of these electrons are spinning up. It has not paired with any of our downward spinning electrons. Let's go ahead and look at zinc. Now, we already know, or hope, that zinc is going to have to end with a 3d10. And we would say 3d10 is the identifier for zinc. So once again, we'd have 1s2, 2s2, 2p6, 3s2, we're down to here now, 3p6, 4s2, because 4s has to come before our 3d10, and that last square is the identifier. If we were going to do calcium, well, calcium, if we notice, is way back here. Calcium, we're just going to have to take off that 3d10 because it's going to end at that 4s2. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. All right, it's your turn. You can pause the video, try a few of these, and come back when you're done. Okay, hopefully you're back. So we've been doing electron configuration. Here they're asking which element has the electron configuration 3s1. Well, all you've got to do is go up to this periodic table. Let me clean it up a little bit here. And figure out what's in the 3s. Our 3s is this section right here. 3s1 would be that first one, sodium. Sodium's a very reactive metal because it's got only one electron in that s sublevel. It's either going to want to lose that one to become a noble gas like neon, or it's going to want to do something to pair that one up. What is the electron configuration for lead? Ugh, this is a long one. We've got to go all the way down to 6p. That's our 6p level here, 2. So it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2. Now, this is what's interesting. We've got to get all of these F's in here. So we're going to go 4F14, 5D10, and finally get to that 6P2. That's long. You'll find out in our next video, we've got a shortcut that's going to make this a whole lot easier. I hope this gave you a quick understanding of how to do electron configuration and how electron configuration related to quantum numbers. As always, stay safe out there, be kind, stay curious, have a wonderful tomorrow.